Okay, in this video we are going to look at trigonometric integrals. And if we look at this first example, I'm trying to do the antiderivative of cosine to the third power. So if we try to use that power rule, think of this as the integral of cosine of x raised to the third power. I need to have, this is like u to the third power, I need to have the du in here. Remember, the du would be negative sine of x, and I don't have that. So this is the problem we come into when we have just a single trig to a power, because we don't have that du part. So the nice thing about sine and cosine is that they are the derivatives of each other, with a negative or positive difference. So here's what we're going to do. We're going to split this cosine up. I know that if I hold one cosine out, that can act as my du. So I'm going to have cosine of x dx be like my du part. And then what's left over is cosine squared. Now, what can I do with cosine squared? Obviously, cosine is not the derivative of cosine, but cosine squared, I can use that Pythagorean identity. Remember, we have sine squared plus cosine squared is equal to 1. So I can use that Pythagorean identity and replace cosine squared with 1 minus sine squared. So this is what that looks like, 1 minus sine squared. And I still have cosine outside of that parenthesis. So what happens is I'm going to split this up into two different integrals. So if I distribute the cosine of x, I'm going to have the integral of plain old cosine of x dx minus the integral of sine squared x cosine x dx. So this allows me to do the antiderivative, right? I know that the antiderivative of cosine of x is simply sine of x. And then here, I'm using my u is my sine of x, and my du is cosine x dx. So this is just integrating u squared. So I can do minus 1/3 u cubed plus c, or in other words, minus 1/3 sine cubed plus c. And that's how we can get around that whole problem with not having the du. So that's going to be our approach to all of these. Is I'm going to be holding out either a sine or a cosine and making the rest of that using the Pythagorean identity. Now that only works when I have either cosine to an odd power or sine to an odd power. So that's what these guidelines are talking about here. So this first one is talking about when sine is to an odd power. Remember, 2k plus 1. That's just our general way of saying a sine to an odd power. And cosine could be anything. It could be even or odd. So if sine is odd, then we're going to hold out a sine dx and then convert the rest of those sines to be like a 1 minus cosine squared. Now, it doesn't matter what this cosine power is, because my u is going to be cosine. So it doesn't matter what power it is, whether it's to the third, to the second, to the fourth. I can do the antiderivative of that. As long as I have my du, then I'll be fine with that. Okay. The other situation is if cosine is to an odd power. So you see, that's like this, and that's like what we were just doing. But again, I could have a sine in there already to whatever power I want. Okay, because all I need to do is make sure to reserve one of those cosines of x's as my du, and then convert all of the other cosines to be sines, and using that Pythagorean identity. Okay, so that's the idea behind that. Now, if both of them are odd, then you can pick. It doesn't matter which one you reserve out, and you can pick that. The other problem we come into is, what if they're both even? Okay, so if both powers of sine and cosine are even, then we're going to use a different identity, the half angle identity. All right, so this is 1 minus cosine of 2x over 2 is equal to sine squared All right, and cosine squared is equal to 1 plus cosine of 2x over 2. So when you have either an even power of sine squared just by itself, even power of cosine squared by itself, or if they're both even, then you have to use these identities. So these you want to commit to memory. All right, let's do an example, another example. Let's look at sine. Okay, so sine is to an odd power, so we're in luck. We can just reserve one of those signs for our du. Okay, so this is the du part. All right, and so then we're going to make this is essentially sine squared of x raised to the second power, right? So I'm going to change sine squared of x into 1 minus cosine squared. Now, since it was to the fourth power, that's also squared. So we didn't have to deal with that before. So we have to do a little bit of algebra here and distribute. So I'm going to have 1 minus 2 cosine squared of x plus cosine to the fourth of x. And this is, each one of these is multiplied by the sine of x dx. Don't forget that. So we really have 3 separate integrals that we're going to do. So we're going to do the integral of sine x dx. That's just that times the 1, minus the integral of, I'm going to put the 2 outside here, cosine squared x sine squared, or sine x dx. And then the integral of cosine to the fourth x sine x dx. All right, so we got all of those written out. Antiderivative of sine x is negative cosine x. All right, and then here our u is cosine, and we're using the du as sine, negative sine. Okay, so this negative is going to be borrowed from there. Alrighty then, so we really have a positive, let me write that out better. I'm going to have a positive 2, u is cosine, so this is like u squared du. And then here, this is going to be a minus u to the fourth du. Okay, so the signs change because our du is negative sign, and then we just change them to u. That way we can just integrate. So this is going to be, when I integrate, I'm going to have 2 times 1/3, so that'll be 2/3 u to the third. And remember, our u is cosine, so that'll be cosine to the third. Oh, I put squared. That's not what I want. Cosine to the third power. Minus, when I do the antiderivative here, that's 1/5 cosine to the fifth x plus c. And then I'm going to also bring down this minus cosine x in front. Alrighty, so that's our whole answer all the way down there. Okay, so we got around that power of sine. So sine and cosine, they are derivatives of each other, so that's what made that nice. The other thing that goes on with derivatives and whatnot is secant and tangent. So remember that, I'm going to give myself a little bit more room here. Okay, so let's remember that the derivative of tangent is secant squared. Okay, so let's write it like this. And then the derivative of secant, and notice I'm using the u's just because it can be anything, is secant tangent. Okay, so even though they're not exact derivatives of each other, they have each other within their in the derivatives. Okay, so also the nice relationship between this is the Pythagorean identity that secant squared is equal to 1 plus tan squared. Okay, so this is the other nice relationship that allows us to work with secant and tangent integrals. Okay, so the thing that makes this different than sine and cosine is secant squared would be my du. Okay, so if I have an even power of secants, then I want to reserve a secant squared. And that's what this first one is talking about. If secant is an even positive power, then we want to save a secant squared and then convert the rest to tangents so that my tangent is my u and then my du is that secant squared. Okay, so notice here, this just the 2k, that's our generic way of saying even. Okay, so notice that they saved as secant squared dx. They converted the rest of that using that identity, and then they still have this du. Okay, and then the other option is if I have secant tangent. All right, so if I have an odd power of tangent, and remember this only works if I have also a secant, right? I need to have both a secant and a tangent. So if I have an odd power of tangent, remember this means odd. So I'm going to have reserve one single tangent and one single secant for my du, right? And then I'm going to convert everything else into secants, right? So this was already a secant, and then here the tan squared is going to become secant squared minus 1. So all of these get converted into secants. Okay, so again, you want to keep in mind what's my u, what's my du. Make sure to reserve out that du. If there are no secant factors, okay, and the tangent is even, convert a tangent squared factor to be a secant squared, and then that can be your du. Okay, so if this is even, then we're going to take two of them, convert it to be a secant, and then we've got our secant squared for our du. All right, if we have the integral of secant to an odd power, then we're going to use integration by parts, which was our last lesson. So that you can see how to do that later. And then if none of this works, then we can just convert into sines and cosines and see if that works. All right, so let's do an example. We have secant to the 6th power. So if I have secant to the even power, I want to reserve a secant squared, right? Notice that we don't just have secant of x, I have secant of 2x, so be careful with that. All right, so if I reserve 2 of them, then that's going to leave me with 4 of them to convert. So these are going to be the ones I'm going to convert. These are going to be the ones that I keep for my du. Okay, so then inside of here, this is going to become my 1 plus tangent squared. And remember, since to the 4th power, that parenthesis is going to be squared. I still have my du. Okay, and then we have to expand. Actually, let's do this. I know my u is going to be tangent, right? Tangent of 2x, and then my du would be, I'm running out of room. My du would be secant squared of 2x times 2. All right, so rather than going through and expanding it with the tangents, I'm just going to go ahead and replace this with our u. Are we okay with that? So that we have 1 plus u squared. And the thing is here we have to account for, we don't have the 2 for there, so we'll have to account for that out here, so we'll need a 1/2. And then this is du. Okay, so this might make it easier. I don't know if it does or not for you. Depends on how you work. But I'm going to have 1/2 in front of all this. Now I can just expand a u instead of tangents. So I'm going to have 1 du plus 2 u squared du plus u to the 4th du. Okay, so these could have all been tangents. You could have done it with tangents, but I'm just putting in the u early, I guess. All right, so moving on. I still have the 1/2. Then I'm doing the antiderivatives. So that's just going to be u plus 2/3 u to the 3rd plus 1/5 u to the 5th, all with a plus c. And go back and just put in your tangent 2x's. Okay, so this is going to be 1/2 tan of 2x plus, if I distribute that 1/2, I get rid of the 2's, so that would just be 1/3 tan cubed of 2x. And then I'm going to have our 2 times 5 would be 1/10. So it'll be 1/10 tan to the 5th of 2x plus c. All right, so it's a long answer, but that's how we use our secant squared pullout. All right, so then let's look at this one. We have an odd power of tangents, and I have a secant squared. So, what should I do here? So, you know, I could use my rule where it says pull out a secant and a tangent, but what would happen if we used u is my tangent and I already have my du? So I think that would be easier in this particular situation. U would be tan 2x, du would be secant squared 2x times 2 dx. And so I just really need that 2 and then compensate for that outside. So that would be 1/2 integral of u to the 5th power du. And so that's going to give me, so I'll have that 1/2 times 1/6 u to the 6th plus c, and then that would be 1/12 u, which is tangent of 2x raised to the 6th power plus c. All right, so I think that's the easier way. However, the intention of this example was to show you how to do the other way. So let's hold on to that. That's one option. You guys can keep that there. I'm going to erase just so I have room, but you guys can keep yours on your page. Let's say we didn't catch that, and let's say we wanted to use the pull out a single tangent and a single secant. All right, so that would mean that I have a tangent to the 4th left over and a single secant. And then for my du, I have a tangent secant. Oh, I want my dx in there. There we go. All right, so I have to convert. This is already converted to secants, but then I need to convert this over to secants. So I'm going to change this to be our secant squared minus 1. And that parenthesis is going to be to the 2nd power. This stays that, and then I'm going to keep this as my du. Okay, so I'm going to expand this. So let's go ahead and do that. So that would be secant to the 4th power 2x minus 2 of these to the 2nd power plus 1. And we're going to distribute that secant of 2x And remember, all of that will get multiplied by this du. Alrighty, so what do we really have? We have the integral of secant to the 5th power times our du. All right, then we have this integral raised to the 3rd power times our du. Just put du here. I'm running out of space. And then I'm going to have just that secant. Okay. So what is our u? Our u substitution here will be our u is secant of 2x. Our du is going to be secant tangent times 2, because we have that 2x in there. So all of these need that extra 2 in front of, and then that 1/2. Okay, so then what do we have? We've got 1/2. Then we've got u to the 5th power du. Then I've got just, I don't have the 1/2 there. I've got u to the 3rd power du. And then I've got another 1/2 u du. And then I'm just going to do the antiderivative. Let's use green. All right, so I'm going to have 1/2 times 1/6. And then I'm going to have 1/4. And then I'm going to have 1/2 times 1/2 u to the 2nd plus c. So what do we have here? We're going to have 1/12 u to the 6th minus 1/4 u to the 4th plus 1/4 u squared. And then I can replace all of these with our secant. So then your question might be, well, how in the world is that the same thing that we got before? So what we could do is change all the secants, because these are all to even powers, change them all to tangents, and then we'll get the same answer. So you can do that as an exercise if you'd like. Okay, but keep in mind that sometimes when you do it by hand a certain way, someone else might do it by hand another way. And you'll get different answers, but that doesn't necessarily mean that you're wrong. Okay, so moving on. Actually, I'm going to pause there. If you want to see more examples of these, I'll do another video.